welcome you all to today's TMS Tuesday, the origins of standards for AGL. This is because of the depth and breadth of this topic. This is a two-part presentation, and Tony Smith, who was very much a part of the very much party to the origins of these standards, and has a unique insight. Well, a pretty unique insight, because I can see Seward there, who's also was also there very much at the beginnings of the establishment of these standards. But what we're covering today is the actual origins of these standards, how they came about, what were the driving forces behind their creation, and why they are what they are today. So you understand the reasons behind them. And back in the day, and Tony will talk some more about this, and no doubt Seward, there was an awful lot of practical research. There was more money to fund the science that went into the development of these standards. And so, and that's a very interesting part of their development, because they're there for a reason. The figures are what they are for a reason. So it's very proud to introduce today Tony Smith, Fellow of the Royal Aeronautical Society, a UK government scientist from the 1950s right the way to about the turn of the century, winner of Aeronautical Society Wakefield Gold Medal, Flight Operations Silver Medal, Outstanding Achievement Award from the IESA North America for the development of the PAPI, the Sabans Wallace Medal, also in 1992. Absolutely amazing career, and to share with us today all of his knowledge and understanding in terms of the development of the standards as it relates to the approach lighting, the runway lighting, and of course the PAPIs, for which he was responsible for the invention. Also on our panel we have Seward Ford, representing North America, and very much party to the process, and working closely with a lot of the people you'll hear about today in the development of the standards, these global standards for aviation. Keith Costel, who is, as we know has been the bedrock of our presentations for this last, I think must be going, but this is almost 2 years we've been doing these now. So thank you, Keith, for help for making this happen. And ably supported by our team of Damon and Felicity, who put these presentations together. So without any further ado, I'd like to hand over to you now, Tony. Please keep your put your questions on the chat line on your screen, and we will have a Q&A session that the panel will will answer your questions after we finish Tony's presentation. So over to you, Tony.
Well, thank you very much for the introduction. I just hope in half an hour's time you don't feel you're disappointed at what you get after that introduction.
I'm sure we won't.
It is, as Robert already said, this whole subject is massive, and in half an hour or so, 40 minutes at the maximum, including the PAPI, we can't cover everything. There's an awful lot I just can't even do other than just mention, to say I'm not going to talk about that today, but they're an integral part of the AGL system, and we're part of research and part of the visual aids panel work. Just to give you an illustration of what I'm saying, I'm not going to talk about intensity control. That's very important, and what's in the annex has good scientific basis, and so there isn't time to talk about that. Or the whole business of standby power supplies, another very important safety issue. And then looking at equipment, why do we have the dimensions we have for the height of inset fittings? Couldn't they be higher? Or they does pose particular design problems, the very limited height that we can have. There's reasons for that. And temperature limitations of inset fittings with aircraft possibly stationary on them, and the whole business of approach light frangibility. A lot of time, about 25 years ago, given to that in the visual aids panel. but no time to talk about all those things today. I just want to concentrate, if I can, on the sort of very much the basics of approach and runway lighting and PAPI. So that's our agenda for today. So if we go to the next slide, please. Right. Well, from the very early days of flying, there was a concern and a need. Pilots, of course, initially the very first flights were in good visibility daytime conditions only. It wasn't long before people said, we'd like to be able to fly at night, but we can't see enough to be able to do that. And to put it in a word, there was a hope, shall we say, between about 1910 and 1940, that somehow some lighting could be devised that would turn night into day, so that pilots could do what they did at night in the same way that they controlled the airplanes by the day. And so we see here stories of examples of, for example, there's a story that when Lindbergh was arriving in Paris, having flown the Atlantic, enthusiasts went out to the landing strip with their car headlights and shone them on the grass to give him some visual cues to land by. There were, at that time, of course, before the 1940s, there were effectively no runways. You had an airfield with grass, and the direction you landed in depended on various things, including the wind direction and other things. And so it wasn't until you got really into the 1940s before we started to see major fixed installations. In the 1940s, there was, and certainly in the military, there was the famous flare path, which was certainly in British application, was what I'd call a watering can with a wick in it, which was full of aviation fuel, and you just lit the wick, and there you got one candela. And a row of these would provide a pilot with a landing direction and enable him or her to land alongside. No point at that point of both sides of the runway. It was one side only, and there were early attempts at some sort of glide slope indicator, but again, very low intensity devices for nighttime only use. And that was, I think it's fair to say, up to the 1940s. That's where the emphasis was, just in nighttime visibility, not low visibility, although the issue was there and some people were doing experiments. But if we move on to the period starting with 1945, well, it's 1944 when ICAO was founded and started to look at issues that were pertinent to international aviation, pilots being able to go from one country to another and getting the same service wherever they went by in all sorts of aids. And so in that period, we start to see money actually being spent on research and development to try and improve lighting. And coming along fast was the desire to operate in low visibilities. The two added one to another, as it were, in the development to not only operate at night, but to be able to operate in lower and ever lower visibilities, finishing up eventually in 0-0 so-called landings. That was the intention. And the money was there to do quite a lot of research. I speak, of course, particularly from a UK perspective, but quite a lot of things I mentioned, similar things were going on in other countries, particularly, of course, in the United States, but also in other countries like France and the Netherlands had significant research resources at this time. And there was a lot of dialogue in conferences, and indeed ICAO sponsored meetings, trying to devise, first of all, a basic runway lighting and approach lighting system. And if you want to look a bit more at the history and the development and how it all happened, if you go to your Annex 14, in the early pages at the front, there is a history of the development, even pre-visual aids panel, of AGL, and you can see when various equipments that are now specified, when they were worked on and developed and then promulgated and put into the standards and recommended practices. It's a good little read if you want to spend half an hour having an overview of sort of time scales. However, in this period, 45 to say 60, there was a recognition, at least in the research world, that before we started to do significant development of lighting, and to get it right, and to be able to say this will do the job properly, there needs to be some proper research and development. And quite a lot of work was done. Certainly in the UK, there was a predecessor of mine, Ted Calvert, whose name is forever associated with the approach lighting pattern that you see on the screen at the moment. He did a lot of work. And one of his tools was actually to do proper perspective drawings of what runways look like on the approach from various ranges and with various offsets. And he had a lot of dialogue with pilots, trying to understand how they used the visual cues to control the aeroplane. And a lot of awfully good work was done in that time to be able to then begin to develop the lighting, both in terms of patterns and in terms of intensity and beam spread performance that was necessary. At that time, we could say there was some sort of operational understanding that the lighting was necessary so that you could have safe and repeatable operations. As far as possible, the pilot not having to do a lot of special training to be able to do it. You'd be able to operate at night with the same workloads that he had in the daytime. This was to continue not only at night, but also increasingly as interest developed in low visibility operations. So between 1950 and 1960, a lot of this good thinking began to appear at airports, initially in demonstration programs, but more and more to enhance capability all the time. There was a push from the industry. We want to operate more safely in lower visibilities. So constantly there's this pressure to enhance and develop the aids. There was a lot of theoretical work, as I've already described, and that was supported by simplificant flight trials and the use, even in the 1940s, of a simulator. Calvert built a very basic simulator in which he could show pilots patterns and get from them an appreciation of how they were using it and what was helpful in them making decisions to proceed or not if the visibility was restricted and so on. There was an awful lot of research going on in those years. And if we go to the next slide, please. No, you've gone too. We're going to go. That's that one. That here's part of. Calvert produced a paper in the late 40s when he introduced a thing called the streamer theory. And here, if you like, is one of his type of perspective drawings. The inner thing you see is the runway. There's the runway, a rectangle, a sort of trapezoid thing with a cross in it. Now the cross is the point in this field of view where if you continue on the approach towards that runway, that's where you will land there if you continue in a straight line to that point. And as you continue down the approach, the runway grows in size, and you can see from the diagram I've constructed how the threshold comes towards you, the stop end goes away from you, the edges move out sideways, the corners move diagonally. The whole thing sort of explodes from that point. And that's very important, because if you understand that is the basic cue by which a pilot aligns with the runway and makes a descent, you can see what he wants to achieve, and you can see where visual aids might enhance the ability to do that. Because in fact, that cross I've shown there, you can't actually say exactly where that is at any significant ranges. It's only when you get really close that you can finally decide, probably when you're inside half a mile, you can really decide by just looking at the runway exactly where you will land. Before that, it's just almost a static picture. But at the latter stages, the runway explodes like this. And this is, of course, very important in the low visibility and in your final landing, which is where the lights are particularly useful. The puddle of uncertainty can cover the whole air runway and more when you're out at several miles. And this phenomena is understood by the fact that we can only perceive movement in our field of view above a threshold of angular movement. There's something like half a degree a second. It is an absolute threshold. If something's moving less than that, you're not aware that it is moving, because the point where nothing is moving is critical. Of course, in aviation, because if you're flying an aeroplane, the one light you're worried about when you're flying at night is the one that seems to be dead ahead and isn't moving, because that's a collision course. And people, sailors, of course, know this as well, that you want to see lights that you can't truly identify, being in transition, moving away from the point where you're going. So this is a well-known phenomenon. It wasn't understood how it impacted pilots until Calvert did this sort of thing. I mean, one other thing, perhaps to illustrate this, if you are in the position of you do a parachute jump, you'll find that if you jump out of the airplane at 10,000 feet, you have a map of the area, a large map, and it doesn't change very much in your perception till you get quite close. And then suddenly the ground rushes up and hits you. And that's a manifestation of this. So that diagram helped an awful lot in deciding what patterns were needed and how the pilot would use them. So closure rate cues, very important, and a stable approach is also critical to a good landing. And so the visual aids, whatever they are, need to enhance the information that the pilot already has to enable him to achieve that aiming point. And in a sense, you could say his task is to make his velocity vector, in other words, where he's going, coincidental with his aiming point. Most fundamentally, that's what a landing is, making your visual, your velocity vector coincident with the aiming point. So if we go on to the next slide. Another thing that Calvert and others showed, and I think Calvert was the first person to point this out. If you look at that diagram there, on the left-hand side, if you come out in the lower visibility and suddenly see a length of lights in the approach, it's an approach lighting pattern, at an angle like that, what's that telling you? Well, it can be telling you two totally different things. If you look at B, where we've now put a crossbar in B, the aircraft is probably on the center line, but rolled. Yeah, the aircraft has got roll and the wings aren't level. But in C, same center line picture, but with the crossbar in, you can see now the aircraft is wings level, but to the right of the extended runway. And so putting crossbars in was fundamental to making the equipment, the patterns really do what's needed. And to put it shortly, all the lighting patterns for approach and runway lighting should either be parallel or coincident with the track you're making to make the landing, or they should be at right angles to it, like the crossbar. That's how you get your most accurate and most useful information. And so with that information on streamer theories and roll bars, another thing that was added in as the developments went along in the 70s was, as they went to lower visibility, it became clearer that in the latter stages, in low visibility in particular, the pilot needed more textual information as it became known in the area where it's doing the flare. The very fine detail and enhancing this streamer effect effectively, and so the touchdown zone lighting was added into the lighting patterns to provide textual information to enable the pilot to make a good flared landing. There's one other thing that came out of the studies as they moved in then to try and more support low visibility. The question was, well, how much lighting do you actually need to see? How far do you need to be able to see ahead if you're making an approach, and with the concept if you get to a certain height on the approach, you must see enough to continue, if not, you overshoot. How do you put into numbers what that amount of lighting is? And the picture you got acquired the name of the visual segment. It's how much you could see ahead of the aircraft, the visual segment. Was there a minimum value for that? On which, bearing in mind at this stage, we're talking about the 60s, 70s, we weren't talking about the ability to actually do auto lands, although that was the goal. There's going to be significant movement at low level to correct, to get onto the center line and land the airplane. Bearing in mind in the 1960s and into the 1970s, the ILSs were subjected to a lot more interference than they are now. You couldn't guarantee that the center line that the ILS gave you was within very close tolerances. I can remember doing approaches in the mid-70s on the then current ILS and the then current autopilot, where when we made contact with the lighting, we were lined up effectively with the edge of the runway. That was the sort of accuracy. So, but that, if you get that situation, then the information about the center line and crossbars is very important, because in the category 1 situation, you may well be significantly displaced and have to maneuver close to the ground, maneuver the aircraft laterally a considerable distance. And the question was, what is the minimum amount of lighting you need to be able to do that maneuver? And that's still a requirement today for category 1. A lot of pilots, of course, have never seen anything other than what's almost a perfect approach these days if they've got coupled approach. But according to ICAO, you can still have quite large offsets when you're delivered by the non-visual system and still be legal. And the pilot can and should be able to maneuver the airplane. That's why the approach lighting design is so important with its center line and crossbars. Why that is so important that is there. So the segment that eventually was lighted upon, I was told, I wasn't part of the discussion, it was before I started working in this area in the early 70s. And I think it's probably the then chairman of the Visual Aids panel, Charlie Douglas, who suggested it, the answer, talking with FAA colleagues. The answer was 150 meters or 500 feet of approach lighting pattern was needed, the absolute minimum. And the reason why that was so, it was based on good, if you like, operational experience trials, if put it that way, that in the 1920s and 30s, certainly in the United States, there were a lot of pilots who had got a small airplane who were making a living doing flying displays and giving joy rides to people. And that required them to fly from one township to another day by day. And there, of course, on occasions, there was low visibility and, well, can I take off? And in fact, follow the road from township A to township B, fly along the road at a height of 100, 200 feet, and be able to do that within the maneuverability of the aeroplane. The answer was yes, you could if you went outside and counted the number of poles that were carrying the telephone wires along the side of the road. If you could see a sufficient number of those, then you could take off and you would safely fly from A to B. And knowing the distance between the poles, which was a fixed amount, you could work out what the actual distance was, and the answer was 500 feet. That's how that 500-foot minimum visual segment emerged. I was reliably told. So that's where that came from, and that's part of the requirement still today if the aircraft is going to be flown manually near the last station for another, not an auto land. As I said earlier, a lot of this early work was done by correspondence and special conferences, and indeed within general meetings of the ICAO in session, discussing a whole range of things. And it became obvious to ICAO, I think, in the early 60s, there was such a lot of work to do in relation to development of all-weather operations. They had to set up a special panel to look after the visual aids aspects. And so hence in 1961, the visual aids panel was set up. And it's due to them really that we have the Annex 14 that we have today, the work they did starting in 1961. And if you look at the agenda for the first meeting, it only had one agenda item, and that was VASI. And the whole meeting was given over to developing a standard, an agreed standard for that. And so then you will see, as if you look in the front of Annex 14, how subsequent meetings then defined Category 2 lighting with its touchdown zone by about 1965, when in fact, of course, it was becoming clear it was quite difficult to land an aeroplane in those restricted visibilities, less than 400 meters, as it then was, without some addition to the textual information on the runway. And at the same time, there was a parallel lot of lights put in the undershoot, the red ones, which look very much like a touchdown zone, but they're red. They were actually largely put there for two reasons. One, it was a warning that you were within 500 feet of the threshold that you couldn't see at the moment, but you were very close to it. The other one was, it was a gauge that said in that era when the ILS wasn't that accurate, when you did become visual, you better be between the two lots of red lights to be in a good position to do a landing and rollout. So it was a way of checking that the ILS and autopilot was providing you with good enough information to make a good landing. Actually, quite an extravagant way of doing it. If you think of 80 lights there for that information, but there we are. That was the solution they came up with, so then we got to Category 2 like that. When I really started work in this area in the early 70s, we're moving on to looking at Category 3, not so much at that point to develop more patterns, but to say, is the lighting in terms of its intensity, beam spread, setting angles, is it the right equipment for Category 3 operations? And of course, everything in less restrictive conditions. And I was carrying forward the knowledge and experience from night landings, Category 1 landings, Category 2, Category 3. And we did studies, and I say we, I'm thinking in the United Kingdom, we did a lot of studies, mathematical modeling to ascertain what beam spreads were required of the lighting to support category 3 operations, where in fact one of the things that became clear right from the beginning was when you get into those conditions, when you do see approach lighting, it doesn't appear somewhere in the distance. It appears just above the coaming of the cockpit. And by implication, and you can see the geometry, that means that the angles of which you need significant light are greater. You're looking down to a much greater angle than if you're saying category 1, where you may be looking at some distance ahead of the aeroplane when you see the first lights. So it became clear that we needed more vertical beam spread. And I actually ran a whole winter of fog flying at the RA at Bedford, where to demonstrate this need to increase the vertical coverage for category 3, I actually got the lighting modified. We had the Calvert approach lighting pattern with the crossbars. So what I did, the right-hand crossbars, the 5 of them, I increased the setting angle of the approach lights by 3 degrees. And we did something similar with the centerline lights. We had modified centerline lights, had an increased vertical angle, because it was important that we carried whatever segment we had on the approach was still there on the runway. And I wish I still had access to it. It's probably somewhere in the archives. There was a very good bit of film taken on one approach where during the approach, suddenly the right-hand crossbar of an approach lighting system appears, nothing on the left-hand side. Then the second one appears, still nothing on the left-hand side. And then when we got to the third crossbar, we just began to see the left-hand side. In other words, 1,000 feet of distance traveled, about 5 seconds earlier contact by increasing the vertical beam spread. So in the visual aids panel, I presented this data, we discussed it, and it was generally agreed that if we did that, we kept the azimuth beam spreads more or less the same, but vertically we needed more light. So the lighting manufacturers had to increase the vertical beam spread by 3 degrees. And we had to do that because we couldn't just increase the setting angles because although we were looking at low visibility, there was a strong plea, particularly from the United States, saying, hey, a lot of the time we want to see this lighting because we fly visual circuits, probably a lot more than you do in Europe. We want light at low angles. So we've got to keep the light at low angles so that we can see the patterns when the visibility isn't that restricted. So it meant, in fact, the lights had to be redesigned to have a greater vertical beam spread. And so by the end of the 1970s, the patterns and what we have today are based on was based on a development that sort of had its infancy in the 20s and the 30s and so on, but really came into its being from when ICAO started work to have a development of the pattern, which went hand in hand with low visibility. Often by improving the lighting, we're enabled the people who are doing the automatic approach and landing work to reduce their operating limits. And it went hand in hand right the way down to category 3, adding more information into the patterns, changing beam spreads and so on. So we finished up with a mature pattern. It's 40 years old now, but it's there in the annex, in Annex 14. My diagram, you saw 3 developments, category 1, 2, and 3. They were just examples of patterns on the way. And of course, nowadays, there are 2 approach lighting patterns, which are approved by and recommended by ICAO. There's if you like, the one that was originally probably had the greater use. That was the Calvert one with the long crossbars, which I would maintain is still the most appropriate for category 1. But the FAA system, which doesn't have the long, it still has crossbars, but not as long. And that now tends to be the one, for a variety of reasons, that is most generally installed, certainly with new equipment. But that's got crossbars in, and you'll notice if you look at the 2 alternate patterns, the last 300 meters, 1,000 feet of approach lighting is identical, whether you use the Calvert pattern or the FAA pattern. It's only in the outer parts of the approach where you have a distant difference. So if we can have the slide up, please, now, that shows a summary of what I've been saying. As I say, I've had to really dodge around and to say one more thing before that. Just go back to the previous one, please. That one. This is an important diagram. You'll find it in it was in Annex 14 in the appendices. These are the boundaries where an aircraft system, non-visual guidance system, can be said to meet the requirements of category 1, 2, and 3. Category 1 is the dotted line. Category 3 is the hatched area. To get certification for an approach system, the non-visual, you have to be within these boundaries. That means that for the visual aids, we have to provide visual cues within those boundaries. And so it's a requirement when we did our designs. If you take the category 1, whether you're way to the left or way to the right, you should see the same amount of visual segment as you see on center line. Essentially, there will be small differences, it's inevitable, but essentially, wherever you are, as long as you've been delivered within that envelope, you should get the same cues. And as you maneuver within it, perhaps you should retain the same cues. The lighting, in other words, once you've acquired lighting, it should always be there, and as you continue the approach, be certain that it was. And that was one of the issues, actually, I didn't allude to, but we did find in the original design, there were sometimes situations where apparently, due to poor maintenance, had situations where pilots made contact with approach lighting and had an adequate segment. And then as they approached the threshold, the runway lighting was poorly maintained. And as a result, the visual segment decreased. The far point of the visual segment decreased. And so the segment seemed to get smaller. The pilot natural reaction to that was, oh, the aircraft must be pitching up because I'm losing view. So I'll push the nose down. And that resulted in 1969 in a very nasty accident at Heathrow, where an aircraft hit Terminal 2. It was a major disaster. And that actually produced a lot of research money in the UK. And a lot of the funding that I've talked about that happened in the 70s and so on was because of that. But it does raise the point, very relevant to TMS, that the lighting does need to be, all of it needs to be to the standard. You can't do bits of it and maintain some of it. It all has to be, it's of a piece, and it needs to be maintained to the required standards. Otherwise, you can suck the pilots actually into quite dangerous situations. So if we go to the last slide very quickly, and then I should quickly move on to PAPI, otherwise we shall be here all afternoon. There's a summary of the basic operational requirements that I think one can say are met. There's a need for lateral alignment and roll cues from the approach and center line and crossbar. And you need lateral alignment cues from the runway center line lights as well as the runway edge lights to facilitate, in particularly low visibility, the safe flare, touchdown, ground roll. And one mustn't forget takeoff. And takeoffs can sometimes take place at runways where the approach guidance doesn't allow landings to be as low visibility as takeoff. Takeoff can be the design case, in some situations as to how much of the lighting that is required by Annex 14 you provide. When you provide a centre line, for example, that can be your design case, is the takeoff case. The visibilities may be lower than anything you're using for landing. As I say, there's the need for the enhancement of touchdown cues in other than very category 1 and better visibilities. That those textural cues are important for well-controlled flares and landings. As I already just said, the lighting must be designed so that the visual segment, once you've acquired it, does not increase. And that can generally be achieved if the fog is from ground up to a fog top. And there's a good piece of airmanship, basically, that if you're above the fog top, then beware, because as you enter the fog top, you can lose visual cues. And so basically, if at all possible, you don't want to be making decisions to continue above the in a situation where you're above the fog top. At the top of the fog, we will have the thickest fog, and it will gradually improve and get less dense as you approach the ground. So generally, we designed the lighting so you didn't have steps in it where it came and went, and that pattern does do that job, as we now have it. The design case, as I say, is probably, depending on your airport, it's the design case is usually the visibility associated with precision category 3. In other words, that's about intensities. It's the low visibility that drives the intensities you require. But the beam spread should be adequate for non-visual approaches as well. And we have to remember that sometimes, although we're talking about precision approaches, there are runways where operations will need to take place at a non-precision, where the pilot will fly a visual circuit around the airfield and line up with the runway. And in that case, omnidirectional lighting also needs to be part of the pattern to enable those circling approaches to take place safely. So let's leave lighting with, as I say, sorry, a lot of things we couldn't address, but let's just go on to PAPI for a little while. As I say, we've had quite a lot of stuff on that in previous webinars, but just for a few minutes, just to look at PAPI to say, why do you need a visual glide slope indicator? Well, one very basic thing is if you want good landings, then you have to have a stable approach. The aircraft should come to the runway in a very stable situation, both in its rate of descent and in the direction in which it's pointing. Of course, you have things like crosswinds and so on to contend with. Basically, a stable approach is your best hope, both for a good landing in terms of where you land along the runway, but in terms of safety. Safety is built in if you stabilize the final approach. But unfortunately, there aren't any precise alignment cues in the vertical plane so that you fly an accurate and stable approach. You need height and height rate information, in other words, changes in vertical position, to be able to do this. And it just comes to mind, I did a trial once where it was actually helicopter flying. It doesn't matter very much. They were flying non-precision approaches to a runway, and in the approach there was a manufacturing facility, and the facility bought a crane with a very long jib, which was sticking up into the approach area, and the owner refused to put a red light on it because he said it wasn't a fixed object, it was moving, and there was a bit of a standoff with RCA. And so one thing I was asked to do was go and look and see, well, what clearances were there actually with these visual approaches with the pilots. They told me they came in on a particular heading and a particular glide slope angle. What I would say was within the last couple of miles, the heading, the track they were making was anything plus or minus 15 degrees from what they said it was, which they assured me was a stable approach and repeatable. And the glide slope, which was quoted, it was that anything plus or minus 2 degrees. And they weren't really aware, just doing a visual approach, that they had such large variations in their approach path. So nailing the glide slope can enhance safety quite considerably. And this leads to touchdown scatter being minimized. And in the early PAPI trials, we showed that compared with VASI, we more than halved the touchdown footprint over a number of operations. The PAPI gives you a much more accurate approach. You can say when you're planning procedures, this is where the aircraft will land with much more precision. And that can be particularly important when the landing distance available is a critical factor. There's one other thing, and that's if in the approach there are obstacles and things that are potentially dangerous. Obstacles are one. And I see on Facebook pictures of people saying this is a very dangerous airport because effectively I'm flying down the side of a hill with very little clearance onto a small runway. And when I look, the first thing I say is, where is the PAPI? And there isn't one. And everyone's vexed about safety. If they put PAPI in there, I can assure you that there'll be a great improvement in safety. And I think somewhat less adrenaline pumping on behalf of the pilots having to do that landing. It is important to have, and even if you've got ILS on a runway, there should be a PAPI, I maintain, because I've seen accident reports when the ILS hasn't been working because it's in maintenance or something, and there have been accidents, people landing well short of the runway, hitting obstacles because they've got no vertical guidance on a manual approach. A PAPI, I maintain, would have prevented that accident. Those are the basics of why we need a glide slope indicator. We could add more, but those will do for now. Now, this is how PAPI looks like. This is a diagram from my original report published around the late 70s. At that time, we were looking at having PAPI on both sides of the runway. One of the reasons was because we were replacing VASI, and VASI was on both sides of the runway. And some pilots felt that that was essential, that you had it on both sides. But very largely would drop the requirement. Usually it's now on the left-hand side. It can be on the right-hand side, just to you get the same information. You've got duplicative information there, as you see. But there you are. There are 5 states: high, very high, slightly high, on slope, slightly low, and very low. Now, I had a very interesting discussion. I mentioned Calvert and his involvement in the early days and development of VASI. The VASI was developed in the 1940s because, and it was the form it was because it didn't use any lenses, and there was a great concern about contamination of lenses. And at that time, there didn't seem to be a technology to say, well, we can actually have what we want with lenses. So it was without lenses, which meant, in fact, you finished up with a pink zone as you went through, looking through the slit as you went from red to white. That pink zone actually was not actually very useful. It varied in extent depending on whether it was day or night, how much sunlight there was in the atmosphere, if you like. And I have seen VASIs in the past. Actually, it was in San Diego. Having landed one day on going to San Diego, very aware we were flying just above the buildings down the side of a hill. Very little clearance. A day or two later, I was going along that hill on a freeway, and you could look down on the runway. And as the runway came, we were lined up with the runway. I could see the VASIs, and they were pink, all of them. the upwind one and the downwind one. There was no information there at all. And that was a situation we'd get. And Calvert was in retirement, but I went and sat under his apple tree and we discussed PAPI, and he could see that this was a thing, in a sense, they wish they could have done 25 years earlier with the new technology, the ability to find ways around the problem of the lenses misting up when being a high intensity system. And it fulfills the requirement that he agreed with. There's a glide slope indicator needs 5 discrete steps. You don't want continuous information, very high to very low. Pilots want this. This is a digital system. You're either on slope, or you're slightly high with a click, or you're very high with 2 clicks. It shouts at you. It really does. If you've never flown it, if you transgress a boundary, well, you may be having your attention somewhere else. It will shout at you. And during the evaluations, we saw that when we were doing it at Heathrow, pilots reported they got into a wind shear situation below 200 feet. And the first thing, and this is before there was instrumentation in the aircraft, the first thing that told them they were in a wind shear was the PAPI started clicking at them. And so it proved to be a very good design. Where did it come from? It came out purely out of the R&D world. In 1973, the Royal Aircraft Establishment, where I worked, some colleagues were asked to look at the concept that was then evolving of a city centre airport, small runways with steep approaches. The steep approach for 2 reasons: noise abatement and also obstacle clearance. The concept was that you'd have an aeroplane that would make a 6-degree approach. It would be a 100-seat aeroplane, 6-degree approach, capable of doing a coupled approach down to 100 feet, in other words, equivalent to Category 2 operations. And then from 6 degrees, the pilot would manually fly the aeroplane, flare and land on a small runway. So we set up a small runway. We painted a small runway on our big runway, and but how were we going to demonstrate whether 6-degree approaches could accurately flown to 100 feet would actually work? Well, there's no 6-degree ILS that one could possibly use, didn't exist. No autopilots that would fly at 6 degrees, even if we could have modified the autopilot in our aircraft to fly at 6 degrees. So the only thing was, the question was supposed to be, can you think of a visual aid where the pilots can fly the approach from 1,000 feet down, and so the approach will look like the aircraft is coupled to an ILS down to 100 feet, and then we'll look at the capability of the pilots to flare below that. So in about a fortnight, I came up with, I happened to have, because we were looking at Varsi equipment, our manufacturer had come up with the idea of using lenses, but he putting a deliberate pink zone in. I took the pink zone out. We had 4 of those units which we were evaluating, and finished up with after a little bit of alternate layouts, came up with PAPI in a matter of 2 or 3 weeks. We used that throughout the STOL program, and we did it for a whole lot of angles. We looked at, I remember doing approaches at angles of 15 degrees down to 100 feet. And that was quite an interesting, exciting experience. But we were able to show that we could get very stable approaches if we could have an autopilot in the future, flying at 6 degrees, and then the pilots could land the aircraft quite satisfactorily off that. So that's where PAPI came from. And as we came to the end of the program, the test pilots I worked with at the RA said, "This is such an improvement on Varsi. Why don't you go both to the civil and military authorities and promote this? We'll support you to get Varsi replaced by PAPI." And so that then launched into a program in the UK, which lasted about 10 years before we finally got in ICAO. A lot of trials in a lot of airfields, comparing with Varsi on one side, PAPIs on the other, places where there was nothing at all, a whole range of aircraft from very small fighter jet aircraft actually right through to 747s. And as I said earlier, we sometimes got comments about, well, I picked up wind shear during the approach. And one day, a pilot returning to Gatwick, who had not read his NOTAMs because he'd been to Australia or something, and he just found the last leg back into Gatwick, London, having been away for about 2 weeks. And when he went into the crew room, into his offices, he said, there's some lights on the left-hand side of the runway near the touchdown point, red and white. And if you maneuver up and down, it gives you a glide slope. It gives you a 3D glide slope. So he self-trained himself in about 2 minutes, which demonstrates how little training you need to use this aid. So that's the origin of the PAPI. And I think there is one more slide to look at. Yeah, this, just to remind you, you find it in the Annex 14, the 4 sectors, originally 2 degrees 30, 250, 310, 330. And the thing about those lines define a line in space which must be precisely set up. It must be at that angle to a very tight tolerance, 1 or 2 minutes. You should aim to be able to do it within a minute of arc, but certainly ICAO does say, well, 3 minutes. But that isn't the design aim. The design aim is to have it as close to the ideal as possible, and the colour should change from red to white in less than 3 minutes of arc. That's the limit. But from my experience, our basic original equipment, we were managed to achieve with a really quite a basic design, 1 to 1.5 minutes of arc. It's achievable. And if you are responsible for procuring equipment, ask the manufacturer to set up a trial where you can actually view the PAPI you're proposing to buy from a range of at least 1 kilometre and see that you can get this complete change from one regime to the other well within 3 minutes of arc. I see some reports these days. I think some of the PAPIs out there perhaps haven't got this sharp transition, and it's made up not only of the colour change, but also the intensity change. If you look at the original documentation, there's at least a 5 to 1 between the red and white, because the red filter brings the red intensity down. But that, in fact, is part of the design that makes this signal very, very sharp. It clicks. It's in fact flashing. If you take any light and you suddenly switch its intensity down to 20% and back up again, the casual observer will say that's a flashing light, although it never goes out. But that big change of intensity is important. And I have seen light designs, that's more modern designs, where perhaps the manufacturers haven't got the airmanship experience and knowledge that they've modified the specification. And ICAO would have hopefully allowed it if I'd still been on the visual aids worker. They actually allow this 2 to 1. Or 2 to 1, you're degrading the performance of PAPI. You should have 5 to 1, and there's no reason why you shouldn't have. Ask your manufacturer to provide it, and also ask the manufacturer to demonstrate that you can have a transition that is well less than 3 minutes of arc between the two, the red and the white sector. You'll see there, for small airfields, an abbreviated PAPI just of 2 boxes is perfectly usable. As I say, we've talked about PAPI, a lot of the details about where you put it in other things, and there isn't time to go into that today. So I say I've spent most of my time on the approach and runway lighting because I haven't really addressed that before. The PAPI is just a bit of an update and a refresher. But there we are, and I think that's probably a good place for me to stop. Bearing in mind we have been going for an hour, except to say here is a good example of what the lighting does for you. Robert provided this. He picked these up somewhere. It's very good, showing in the top picture you see in fact, it's a Calvert system. That arrowhead makes it very conspicuous where the runway is. And as you get closer, you can see the pattern. Because this is a shallow layer of fog, you see as you go into the fog, it is actually reducing. You can't see as many crossbars on the last one as you can on the others. But that would be a shallow fog below that. That would probably be a very safe landing, but need to beware if you make a decision above a fog top. And with that, I will stop. I think I've gone on too long, probably, but a lot to cover.
And start video. Thank you for that, Tony. Absolutely fascinating insight into the origins of the standards as they apply to the approach lighting, the runway lighting, and of course the PAPI, which you were so you inspired. So that's really interesting. We've got a number of questions here. Probably too many to answer just at this moment, but I will just look through here. Just looking. Which do you prefer, Tony? Centerline and 5-bar or Barrett centerline, and why? Is one question.
Well, of course, being British, I'm going to be prejudiced, don't I, and say the Calvert pattern. They do perform a slightly different function. They are both perfectly adequate for precision approaches. So there are other issues you may wish to take account of, availability of equipment and so on. Either of them that you find in Annex 14 will fully serve today's precision approaches with an ILS, with a whatever it is, a 6th generation autopilot. They're both equally provide. What I would say is where the Calvert has an advantage is if your operations are primarily non-precision or category 1, where you may well need to make significant lateral corrections when you go visual. The longer approach crossbars do provide a somewhat more sensitive and usable cue than the rather shorter bars that are in the FAA system. So take your choice there, really. But bear in mind that as we move forward from ILS into other glide slope guidance systems, those systems are liable to be licensed for operation, cleared for operation, as long as they deliver the aircraft within those envelopes that I showed. And if you look to the category 1, it's a pretty wide envelope. It's a pretty wide barn door at decision height. You can be delivered well off center line. And I think a lot of pilots currently flying the line have never experienced that. But if they were launched into a system where it was category 1, according to the book, but suddenly they have to make significant lateral corrections, they might wish they'd got the Calvert system. But really, it's we're talking small benefits here and there with particular cases. Either will do a good job for the most of the time.
Right, thank you. I've got another question here. In the displaced threshold situation, shall the runway center line in the pre-threshold area be extinguished during approach, or could it be displayed together with the approach lights?
Well, because it can be extinguished and it can be left. The problem if you start switching things on and off for individual, you get a landing and then you get a takeoff and so on. It's that requires someone to stay with it all the time, make sure that you've got the switch in the right place. In many ways, I think it's preferable to have a pattern which sits there for the whole time the the airport is operational. In other words, as soon as you're open for business, you switch it on, it stays like that. So you don't. This is why intensity control, I didn't mention, why it's important in intensity control to have fixed settings, 5 or 6 settings. Because if you don't, you'll have a continual dialogue between controllers and between pilots as to turn it up a bit, turn it down a bit, and different pilots will have it differently. You have no control over it, and at times you may be very suboptimal. It's better to have digital fixed changes in your system. So by all means, yes, switch it occasionally, but don't set it up so that between a takeoff and a landing you switch it on or off and back on again. I would suggest that's not operationally a good thing to be doing.
Thank you, Tony. Next question: is it advisable to have halogen approach lights and LED runway lights for the same runway?
Well, a mixture of
a mixture. So we're talking about a halogen approach and an LED runway lighting on the same runway.
Well, in theory, that should be perfectly acceptable, because ICAO is quite clear. It doesn't tell you exactly how to provide the equipment. It says this is the operational requirement. It tells you a beam spread. It tells you an intensity. It tells you a color. But beyond that, individual states have the option as to how they actually achieve that. And so the requirement as far as in the approach and runway lighting is the beam spread the appropriate one according to Annex 14? Is it the right color? And is it the right intensity? And so you can have different light sources provided the intensities are matched. And I can remember having a discussion in the visual aids panel again with, I mentioned Charlie Douglas earlier, who really was the grandfather in many ways of the early years of this, worked for the National Bureau of Standards in Washington. And in the United States, he was the founder of all knowledge. And he insisted that a candela is a candela is a candela. It doesn't matter what the light source is. If it's 20,000 candelas, it doesn't matter whether it's an LED, 20,000 candelas, or a tungsten halogen, 20,000 candelas. It'll give you the same service.
Thank you. Question from Sebastian. ICAO doesn't have many installation tolerances. FAA is more descriptive on this matter. What is the industry practice in terms of tolerances during construction, for example, in the positioning of lights to achieve specific spacings, for example, maximum 7.5 meters, 15 meters, 60 meters, etc.?
Yeah. Of course, as far as possible, you try and match it. But take runway edge lighting, if you like. If there is a, I don't know, there's a crossing roadway, and where you want to put the next light is in the middle of the roadway. If you put it a few feet upwind or downwind, that really isn't tremendously significant. But I wonder whether is Keith online?
Keith is there. Keith?
Yes, I'm online. Yes,
What
certainly.
What his comment would be on this about?
Well, I think really when it comes to the the tolerances, there is some guidance, and Sebastian is quite right. The FAA are very specific, and whereby ICAO are very generic in their statement. They say equally spaced rather than specific distances. And when we come to installation, if we're looking at 7.5, or remember then when we start to look at distances, say for example 60 meters, it's half 60 meters is 30, half of is 15, half is 7.5, and half again, etc. Whereby Sebastian is correct. If we're looking at, say, for example, taxiway centerline and or taxiway edge lights, and we're looking at around the bend, it will depend upon the radius of the bend. So the distances of those 30 meters, 50 meters, 7.5 will be according to the radius of the bend, and which is more specific, where as ICAO say they are very generic in the statement. And basically, because in ICAO it is more, they are more of an operational standard organization. This is what you must achieve, but not the details of how to achieve it. The FAA have gone to that extra step to say, look, okay, this is what you have to achieve operationally, but the guidance is this is how you do it. And a typical example is a runway guard light. ICAO say, for example, the runway guard light, it shall be seen, it shall be adjacent to the runway holding position, and they shall be seen by the driver of an oncoming vehicle or the pilot of an oncoming aircraft. Well, there are different sizes of aircraft. There are different people, different vehicles. And when we're looking at the sizes of aircraft and the pilot's position in an aircraft, you know, compared to a Cessna and a 747, then clearly the FAA have to go to that next step and then say, no, hang on, we'll tell you the angle, and this is the center of the beam, and this is the crossover point at the center line of the taxiway at this distance. So you know exactly how to angle your runway guard lights, for example, because of the guidance that are given by the advisory circulars from the FAA. So I would suggest to anyone who is looking at installation is to look at the requirements of ICAO in accordance with the annexes and the design manuals, etc. And if you want more detailed information, look at the advisory circulars in the FAA, because you can go to www.faa.gov, and go to the 150 series advisory circulars, and there's some excellent documents, and you can download that information in PDF for free. So that would be my answer to that. So that, you know, so that 7.5, 15, you know, 30, 60 meter, it is a general guidance for operational purposes, but it doesn't have to be exact. You know, it will be according to the radius of the bend, for example.
Thank you, Keith.
Okay.
Jyoti would like to know, wants to understand, perhaps one for you, Tony. Where did the 3 degrees come from? Why 3 degrees as a glide slope? Generally speaking, is it?
Why 3 degrees? Put my thinking cap on. I think it's one of those things that, you know, goes back to the very early days of flying, that it's a compromise between you know, coming down too steep and then having to get rid of that rate of descent later on, and dragging in forever, you know, low down. It seems to have settled on 3 degrees. I have to say, it's one of those things that you can probably find old reports explaining why go for 3 degrees. I think it's largely driven by piloting considerations, aircraft handling, and so on. You know, rates of descent and that are acceptable, and so on. And it tends to come. But of course, when you say 3 degrees, that's what was settled on for precision approaches. But for non-precision approaches and lots of general aviation, And if there's no glide slope indicator, pilots fly all sorts of approach angles, as I said in my illustration of the helicopter approaches, and they're quite happy with it. You know,
Okay.
you can have quite a variation, but if you're going to set up something like a precision approach system, you've got to nail certain things to the ground, and you know, in other words, your ILS, what angle is it going? You couldn't build an ILS for 3 degrees and 6 degrees. You had to choose an angle. And very early on, that was about the sort of angle that generally people made with bigger, heavier aircraft. That's the sort of angle. Bearing in mind they've got a flare and all the rest of it and that. It was sort of, I guess it came out of operational experience very largely.
Okay.
So they chose 3 degrees.
It also came with, you know, with the aircraft, didn't it? When, you know, we're talking about the airfield facilities and, you know, the etc. But when you come to the actual structure of the aircraft, the aircraft land on undercarriage. The undercarriage then has to be of a certain structural strength. And for it to be of a certain structural strength, then of course, when we're looking at the design of aircraft, then aircraft has an all-up weight. And if you had to have a very, very structural, heavy, you know, solid undercarriage, then the all-up weight would be increased dramatically. So there was a balance there, wasn't there, between the operational, the need for, you know, the flare and the actual landing load and the tires. You know, because when you're looking at landing, you also look at the footprint of the tire that is attached to the undercarriage, the structural strength of the undercarriage of a particular type of a particular aircraft, and you look at the range of aircraft. So the aircraft element came into that equation. That's what I'm saying.
Yeah, that's what I was saying. Really, there's a whole lot of parameters that when you put them all in a bag and shake them all up, you come up with 3 degrees being a number we'll adopt as a good overall compromise. You've got to choose something.
Yes.
And for most people, for various reasons, whether they're an undercarriage developer or a pilot or whatever, it was an acceptable number that was achievable and seemed operationally to be a pretty good number. So that, I think, it's very largely out of operational experience where that number came from. Right.
Okay. Right. So coming back to next question. Gerard Lawler in Dublin would like to know, do you see dual PAPI installations as providing additional roll guidance information and resilience if one set becomes out of calibration?
What, the one on both sides?
Yes, yes.
Yeah, that was some of the old bold pilots, of course, who've been flying Vases for years. They always said that, well, Vasi gives you good roll cues because it's on both sides, and that is true. It's because it's effectively defining a long horizontal line. But then I would say the glide slope indicator is not a landing aid, it's an approach aid. And where you're really concerned about wings being level and so on, as you enter the flare and so on, you get that from the view of the runway. And indeed, this is where the touchdown zone lighting comes in low visibility. That gives you the information you need to keep wings level and you know, where out on the sides of the runway. It's not in your central field of vision anyway. There, it was. I think it was quite a strong influence of old pilots and what they were used to. There was a lack. Let's face it. When they started their flying, perhaps there was a lack of visual of good roll guidance information. So PAPIs started to appear in the late 40s. They did give you a good cue, a nice bright cue as well. You know, when the approach and runway lighting was still at a very infant stage. So they wanted to hang on to that because it had been a very useful aid. And yeah, But gradually, I mean, when I started in this, we also had on the threshold on the corner of the runway, we had what are called sodiums. That was the first high intensity approach lighting, certainly in Europe. In the mid 1940s, the manufacturers of floodlighting produced a low pressure sodium floodlight. It was about a good 30 centimeters square. It was a big device, but it was found if you put one of those at the corner of the runway, then that was a very good way of finding the airfield in the sort of murky conditions that pertain quite often around sunset in places like the United Kingdom. And that was the first high intensity lighting. So, but then that got dropped 50 years ago because other aids came along, which did the job even better. And
Good.
I think that's true. We don't need it on both sides. Although I know in the military world they still perhaps. I mean, if you didn't have any approach lighting, you might well decide it's an operational decision. You might decide to have that roll information would be useful, but generally we've got approach lighting.
Okay, Paul Fraser Benison. Well, hello, Paul. Well, one of our friends out there has asked UK CAA Cap 168 edition 12 chapter 6, which I believe was published last year, introduced changes to PAPI settings, UK PAPI settings for UK participants. Has this affected you? Talking about, I think the minimum intensities for a PAPI now in the main beam is 85,000 candela for a white, which is considerably more than ICAO.
Yeah, that in fact is still the original specification. That's the specification that ICAO adopted back in 1985, and its subsequent activity in the visual aids panel stroke visual aids working group, I suspect, should I say, I suspect there's a certain amount of, shall we say, commercial interest crept in here, and perhaps a certain lack of airmanship and aviation knowledge. A good optical designer in a lab somewhere thinks, oh, it'd be a good idea to have the same intensity in both segments, and that just isn't true. In fact, it's false.
Yes, thank you. I think that's something we need to be taking up with the visual aids working group. So Andrew Badham, I see, is on this call. I wonder if we could discuss this with you. A couple of points, I think, like that. Len Ellerchuk has asked, please could you provide information about harmonization of PAPI glide slope with ILS systems by increasing from 20 minutes to 30 minutes. We generally have P2 systems, but have seen an advisory circular where going to 30 minutes is best for P3 only. So it's very specific. I think, do you want to take that one offline, Tony?
Well, I don't know. I think it would be good if Len could provide us with the advisory circular that has been issued, which defines that, because I certainly haven't seen it.
Okay, Len.
So is it an advisory circular from the FAA or an advisory circular from Australia, for example? So there's different advisory circulars. Whose advisory circular and what's its number?
Okay, so Len, if you could let us have that, we will respond to you and we'll publish the response on the website. I've also had asked if we can provide a copy of today's presentation for anyone not familiar. We do always provide a copy of this webinar on our TMS Training Solutions website. So you can access any of our previous webinars going back almost 3 years. I was wrong before, it's 3 years now. And they're all listed by topic. So if you have a specific interest, like for example, PAPIs, they are there and still available for you on our TMStrainingsolutions.com website. I've been asked, Tony, how many nominal miles the pilot must see the PAPI to say it is sufficient? It is sufficient, and it's operating sufficiently and safe to land. So, what in good visibility? How far will the pilot?
The intensity we used originally, was very similar to what was specified with the Varzi, which gave a guarantee that you'd be able to see the lights by day in not low visibility conditions for a range of 4 miles or 7.4 kilometers. That was a sort of design, it's sort of built in. And if you consider 4 miles on the approach, an approach of 3 degrees, it's 300 feet a mile, so that's 1,200 feet. In other words, you can guarantee to be able to use the glide slope. You probably come off a may have come off a stack where you've been waiting to land. You've been vectored in and positioned, probably flying level, at a height something over 1,000 feet, depending on the operation. So you intercept the glide slope signal at about 4 miles, and you can start descent at that point. And as I said, there's no reason not to if you've got the information. It's good because you start to stabilize the approach as you do all your flap changes and get the gear down and all the rest of it.
Does that refer, to the, to the outer market, the ILS outer market concept? As a nominal visual.
In other words, effectively, the final, what do you call the final approach? On a good day visibility, you've got glide slope information.
Yeah.
Good. Well, look, thank you, Tony. Thank you, Keith, and of course, thank you to all of our participants today. I hope you've enjoyed it. We are running half an hour over. There are more questions which we will put answers onto our website for, but I'd like to thank you all for your time today. And especially Tony for all this hard work and preparing today's presentation, and a lifetime's knowledge that's gone into delivering it. So thank you very much, Tony. Thank you also to Keith, and thank you Felicity and Damon for helping to put it all together. And I look forward to seeing you all in TMS Tuesday in February. It'll be February the 28th, where Tony will be presenting the taxiway lighting and signage aspects of the kind of the history and development of the standards for airfields. So, well, I'm very excited.
Can I just say,
yes,
if I have in mind the very nature of the start of the whole idea of needing to monitor inset fittings and maintain them was kicked off by the work that eventually produced the taxiway lighting we've got it today, where I went to an airport which was certified and I started taking measurements of both taxiway lighting and runway lighting and found the maintenance standards were appalling. So, within the context of maintenance and so on, the story starts there because I started looking at taxiway lighting.
Yeah. Thank you. So it's very important. And
well, I think it's got I've got a little comment there, Robert, just before, and at least for everybody who's still online, is if they think maintenance, etc., is expensive, try an accident.
Yeah. So, yeah, exactly, Tony. The standards are there for a reason, and it's for those of you, whether you're involved, whether you're designing airfields, whether you're installing them, or maintaining them, or indeed regulating them. It's very important those standards are met. I hope you've seen from today, they're there for a reason. They have been scientifically developed and put in place. And so it's our duty to make sure that they're upheld now and in the future. So thank you very much, everybody, and I'll see you all on the 28th of February.
Yep.
Thank you for your time. Thank you, Tony. Thank you, Keith.
Okay.
Bye.